So we have seen the Urison metrization theorem, and a key role of that was played in by the relatively simple fact that countable product of metric spaces is a metric space, but we saw arbitrary products is not. The Ticonos theorem also has many applications, a very interesting result, but this works for in fact an arbitrary collection. So suppose X alpha in alpha is a collection, this time of compact, or let me state that in the theorem of topological spaces. So the theorem says that if X alpha, if each space X alpha is compact for all alpha in A, then the whole product is compact. Now if this was a countable collection and we were dealing with sequential compactness, you can do this by a diagonal argument. Namely that if we have a sequence, you can find a subsequence so that the first coordinate is compact, a subsequence of that subsequence so that the first two are compact, and so on. And this will give you the result. But in fact, the general result, well, we'll use there are many proofs of it, but they all use some form of axiom of choice. Okay, so we'll use something called Alexander's subbasis theorem, which is a nice striking statement in its own right, which is the compactness criterion. So that's what this theorem is, Alexander subbasis theorem. So instead of nesting a proof, let me just say we use this. And what the theorem says that suppose X is a topological space, B a subbasis such that every cover of X, so it's automatically an open cover because this is a subbasis. So every cover of X, well, I didn't say why it's an open cover, by elements of B, by subbasic open sets. Elements of B has a finite subcover. Then X is compact. So it's enough to look at rather special class of covers, those that are covered by subbasic sets. Okay, and because basic sets we can pass to smaller sets, subbasic is more complicated. We have to take intersection and union. This is far from obvious, but it's true, and there's a nice proof of it. The first step of which uses Zorn's lemma, namely, suppose not, let U be a maximal open cover. So it's not compact, so there is an open cover, and so we take a maximal open cover such that U has no finite subcover. Okay, it's crucial it's maximal, so we made it as big as possible. Such a maximal open cover exists by Zorn's lemma because if I have open covers with this property of having no finite subcover, and this we have a collection of these which is totally ordered, the union of these will also be an open cover clearly and will also have no finite subcover. So this is exists by Zorn's lemma. Let me say exists by Zorn's lemma. Now, by hypothesis, since this has no finite cover, as U has no finite subcover, so U intersection the basic open sets is not a cover. Okay, Well, you may think this should be very small. It's been taken to be maximal. We still don't know. This could be empty. But what we know is that this is not a cover, because if it was a cover, then U intersection B will be a cover which is contained in B and hence have a finite subcover. Okay, so let X be a point not in any set in U intersection B. So, but U is a cover. So then there exists U in U such that X belongs to U, and B1 Bn in B such that X is in B1 intersection Bn and just contained in U. So this is simply because it's a cover, and because it's a subbasis, there's a point, there's an open set which is an intersection of subbasis elements which contains the point X and is contained in U. Okay, so now, well, let's look at U union Bi. Now just observe that Bi is not contained in U. For all I. Okay, because if some Bi was contained in U, then it would be contained in B intersection U, and X would be a point in that. But X is not covered by such a set. Okay, so by maximality of U, remember it's maximal in containing no finite subcover. So by maximality of U, U union, let's take the single element Bi, has a finite subcover for all I. Say, well, what is this finite subcover? It can't be contained in U itself, so it has to include the singleton Bi. Say Bi and then C, let's put a superscript I1, Ci2, Cimi. Okay. So for each I, we have such a subcover. So now what happens is that and then just look at B1 intersection. We're going to get a contradiction from this because say B1. So let me just spell that out. First let's spell this out for each thing. So then Bi union Ci, so superscript was I, C1 I1, so for a fixed I we have Bi union Ci1 union Ci2 union Cimi. This is going to be equal to X for all I. So therefore, if we look at the intersection of these, B1 intersection Bm, all of these, union, let's look at the union over I is 1 to M, N, and union, and J equals 1 to Mi of Cij. So we are looking at all these collections and union of these, and intersection of this is X. Why is that any point in X? It's either in all the Bi's, in which case it's in the first term, or it's not in one of them, in which case it has to be on the second kind. Formally you can play around with De Morgan's law, but you can just see the cases. You're either in all the Bi's, you're in the left term, or you're not in at least one Bi, then you're in the corresponding right hand side and hence in this full union. But now we know a lot about these. So each of these is in U, the collection U, and this is contained in U. Okay, so because that was our construction, so thus U and Cij, so U, let me put it this way, U union, if I look at Cij, 1 is less than or I is less than or equal to N, and 1 is less than or equal to J, is less than Mi. So I take that single set U, which I'll write a little more clearly, single set U union this is a finite subcover of U. So this is a contradiction. This proves the Alexander subbase theorem. Okay. So given this, it's not hard to prove Ticonos theorem, because Ticonos has a very nice subbase of Ticonos. Okay. So consider, let whatever it is, U be a subbasic open cover for the product alpha in A x alpha. Okay. So now we consider, so what are subbasis elements here? So the subbasis elements, well, they correspond to, in a very natural way, indices alpha in A and a subset, whatever I'll call it, U alpha beta at contained in X alpha. Namely, it's the product of this with all other indices alphas. Okay. So now we can say a couple of cases. So if for a fixed index, well, we claim, let's just claim that for some index, that is for some index that appears in this collection, the sets U alpha beta with that index cover X alpha. They correspond to space. Okay. And that is clear because proof, if not for each index, so pick X alpha not in any set corresponding to that index. Yeah. And arbitrary if no sets correspond to that index. Okay. We'll go over this in a concrete case. Suppose our indices were integers. Okay, and then what we want to do is we want to pick an element. So our if it was a plane, we would have sets like this or sets like this. Okay, so we have sets which are kind of cylindrical. Let's look at them piled up at an index. We have various cylinders at that index, or some index we have no cylinders at all. Now look at just the sets corresponding to these cylinders, the sections. Claim is that for at least some index, they cover the whole set in that coordinate. Because if they don't for any given index, then I can pick a point which is not covered by this. And if for each index where there is at least one such cylinder, I can pick this coordinate, then I'll get a corresponding set. I'll get some such coordinates. Suppose I could do that, and then I pick arbitrarily where there are no restrictions at all. Okay, we see that this point X alpha is not covered by U. Okay, so if I look at this coordinate, because if it's in U, it's in U alpha for some alpha, that will correspond to some index, and then that particular coordinate will be covered here. Okay, so this was the proof of claim. So this is a contradiction. Okay. Now, of course, if the sets corresponding to some index cover X alpha, some index, let's say alpha naught, cover X alpha naught, then these form a cover. So these form a cover of the whole space product alpha in A x alpha, just those which are correspond to one index x alpha naught. Okay, and now so what are these sets? If the sets, these are going to be u at alpha naught, so it's going to be some u beta contained in x alpha naught cross so something. Okay, don't want to write out the elaborate notation. These are sets which are except at alpha naught, the whole space. At alpha naught there are some u beta. So if the u betas cover x alpha naught, then just these sets form a cover of alpha naught, and u betas have a finite subcover. So now we are done. I have a finite subcover. This gives a finite subcover of the whole cover. Okay, the proof, while complete, does not have clean notation, so let me repeat it. We have once we have the subbasis theorem, it's quite easy. Namely, if I have a cover of subbasic open sets, so the subbasis elements correspond to indices alpha and a subset u beta alpha contained to X. So beta is an index of secondary index like we had J previously. So for any fixed index, we can have any sized collection u beta, and set corresponding to this means that is, so I should not say script u, I'll just say u beta alpha. That is, we have V equals the product. So such a corresponding set is, I won't take alpha, gamma in A of Z gamma with Z of alpha is U alpha. So V alpha beta is this product, is Z gamma alpha is U alpha beta. Z and Z gamma is X gamma for all gamma not equal to alpha. Okay, so we have this V alpha beta is this cylindrical set covering it, and I look at what are the coordinates of the cylinder, and I claim that for some coordinate of the cylinder, the corresponding sets in that direction must cover. And the reason is, if that none of them do cover, then we can pick a point which is not in any of those in that cylinder, and we can do it for each coordinate of the cylinder, and then we put these together as a tuple. There will be points which don't correspond to a cylinder at all, in which case we just take an arbitrary point in that set. Okay. So we have to assume these are non-empty. Okay, if one of the sets is not empty, the product is empty, so we are done. Otherwise we just pick an arbitrary point. So we have used the axiom of choice here, by the way. And now once we have done that, we just look at the cylindrical sets. So we are looking at the U beta alpha. So here I had scribbled things. So these were the sets which I earlier called V alpha beta. Now if the sets correspond to some index alpha naught, so we are looking at these cover alpha naught, and this is going to be a product. So this is going to be dot 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 with u alpha beta at the appropriate coordinate. Then what we just note is that form a code. So let me correct my notation here. So then I know u alpha naught beta. These sets have a finite subcover. There are finitely many betas, and then I take those betas here and they form a cover of the whole space. Okay, so this proves the Ticonos theorem.